Wooden rod, balsa wood. Balsa wood is one of the lightest rod that you can have. It's commonly used to make the aircraft wing structure. Okay, if you attend the unmanned air vehicle class, it's very often that you will use the balsa wood to build the structure of the small fixed-wing aircraft. Okay. So this was the test done yesterday. So if you could remember, so this test was how many seconds? Over 30 seconds, you have, is it 13.5 times? Okay. So that was the frequency measured yesterday. And now, okay, we're going to remove the apple and measure the vibration of the balsa wood slope. Okay, as you can see already. So it's a frequency rate higher or slower? Higher or lower? The rod itself. Okay. So we have done the test. So this is the fourth test. Okay. So I have a rod made of balsa wood. And then remove the apple. This rod itself is not massless anymore. Okay, it itself has a weight. Okay, so okay. So let's do the experiment again to measure the frequency. 来，昨天的同学要不要跟忙计时？其他同学的一起算。So let's count the frequency of this. This is called compound pendulum. 好，开始了。你没有计时？
没有计时。
哦，其他同学算。我们再来一次。
10秒。
10秒。OK。这里0.8赫兹。昨天这个是多少？67.6。So you can see that now you have the rod itself. It's no more muscle. Okay. So that is relative. Okay. So in that case, how will you analyze this vibration of the rod? Can I still lump the mass at the end? Yeah, so it's not quite true. Okay. 所以要模拟这样的一个复合单板，因为它的质量是分布在杆上面，你不能完全就直接把它的所有质量都丢在杆的末端。OK， 所以这个时候，你就要做一点分析。OK。所以这个时候，你要找自然频率一样的，你要应用牛顿第二定律。但是你用的是角运动。So if you're going to determine the natural frequency for this, you're going to write Newton's second law, but in the angular coordinate. So you first have to determine the moment of inertia using parallel axis theorem, and then later on determine the moment. Okay. So the first thing we're going to determine is the moment inertia to get you refreshed. Okay. So how to define the moment inertia for a rod? We start from kinetic energy. So it's going to be half J naught theta dot squared. Okay? So this is to describe, okay, the rod offsetted from the center line by angle theta and traveling at the angular speed. Okay? So this rod has a length L. as the length, it carries a small mass, okay, Dn. This Dn is then the small length over the total length times the total rod length. Okay, so this is the subject we're looking at. Okay, accumulations of these, okay, will give you the total mass. And of course, you can also write the small kinetic energy for this piece. So it is half the n, the tangential speed squared. So what is the tangential speed? So if this is the radius passing through angle theta, then the arc length will be r theta. Okay? And the tangential speed is then r theta dot. So you can write half the r over Lm times r theta dot. Okay? And then square. So in that way, you could determine the small amount of the kinetic energy stored in the mass. So this is then half. Okay. The only variable is radius. So let's figure out the radius. Okay. So the rest are all constant. So you have n over L theta dot square, and then r squared the r. Okay? If now you're doing the integration of the kinetic energy from r equal to 0 to r equal to L, then you're going to have the integrations of r squared the r from r equal to 0 to r equal to L. Okay? So this one, what's the substitution? Then you can readily find this integral is r cubed divided by 3 by substituting r equal to 0 and r equal to L. So in the end, you have half nL squared divided by 3 theta dot squared. Okay? So this is how you determine the moment inertia. So you might have learned this in the course of dynamics, and this serves as a revision. 所以我们就先把这个反动惯量这个公式给写下来。Okay. So it's all inside your notes. Okay. But this will give you a overview how it's obtained. So this is the tangential motion. A small piece of mass Dm carry the small amount of the kinetic energy, half r theta dot squared times the mass. Then the total kinetic energy will then be the sum by integrating these. So in the end, so you have this expression, and then the mass, the moment of inertia. Okay, remember? We're talking about moment of inertia in this position. Okay? So this will give you the moment of inertia being J naught over J naught is 1 over 3 times mass and times the length squared. And of course, it's going to derive it from some characteristics theorem. Rod moment inertia about the center is mL squared over 12. Okay? But now, the axis of rotation is not at the center of the gravity, but at the tip. So in this case, what you're modeling is, okay, a rod. If you have a self-rotation, okay, this is what you call Jg, mL squared over 12. But now, this one is rotating about the point O. Okay? So it's equivalent to have this mass rotating about point O at the distance L over together, you then have to add this cell rotation and the point mass rotating about the axis by means of m L over 2. This is for your d, and this d is called the axis, the distance between the axis of rotation and the gravity center. So by adding the 2, then you have the J naught. Okay, summing up, then this is ml squared 112 plus 1/4. So in the end, the answer is still 1/3. Okay, so you're going to obtain the same value. Okay. Okay. After you have done this, now we're going to write the equation of motion. Okay. So let's write the equation of motion. Okay. So you now have a rod. Okay, rotating about the vertical axis of the equilibrium position by angle theta. Okay, so in this case, if you are writing equation of motion, you are writing J naught. J naught is the moment inertia about the pivot O, equal to the moment sum about the pivot. Okay. So in this case, what is causing the moment? It must be the gravity. So the gravity will then have the weight mg. Okay， 所以我们现在要写这个运动方程，对于一个复合杆 ，OK， 大家知道这 O 点转动 ，OK， 所以你要写的运动方程是牛顿第二定律，不过是用小坐标，然后这个时候。这个多头边这个是转动惯量乘上角速度，角加速度我们已经算过了。唯一现在还没算的是它的力矩扭力。这扭力从何而来？这扭力是本身杆的重量，杆的重量一定是作用在你的这个中心位置。中心位置，如果这杆是均匀的，就是在中间位置。所以你看到没有？这个位置的这个扭力有多少 ？Okay, how much is the moment here? So you can resolve the vertical force into two components. Okay, this component is what you call mg sin theta. Okay, and the moment arm away from the pivot is L over 2. Okay? And what is the direction of the moment? This direction of the moment is clockwise. How about the direction of the acceleration? Counterclockwise.
Yep.
Yeah, if I take this coordinate of the angular rotation and angular acceleration to be positive counterclockwise, this moment will then be negative, okay? Because it's a clockwise, minus mg L over 2 sin theta, okay? So now you can rewrite the equation, J naught theta W naught plus mg L over 2 sin theta equal to 0. This is your equation of motion. But assuming sin theta equal to theta, now you have second order derivative. 所以同学有人攻数学的这个微分方程啊，二次微分方程，这个时候就用上。你如果认不准这个的话，你可以把它写出写题 ，OK。Okay. So since you have derived the equation already, okay, and you're quite familiar with these ordinary differential equations, you can numerator is NGL over 2. And then the 1 in the denominator is this J naught. And then this J naught is equal to ML squared over 3. So after your simplification, then you have this returned to be 3 over 2 G over L. OK， 来，同学帮我算一下，这个比一比，这个有没有开根到2/3？ OK， 第一次实验跟第4次实验。OK， 0.8， 没有，这个不是这是刚好的大数，0.67。So if you are comparing this, it's going to be square root of 3/2。来算一下，这是多少？再乘上1.5。那我们有没有算错？这是，这是倒过来，3/2，不好意思，是分母。3/2，再跟上3/2。是多少？1.8。这比着呢？0.67所以0.8。
0.83。
0.83，不错啊，这个很接近哦。OK， 所以看到没有？所以你们刚才两组实验，一个是简单单板，就是英模单板，一个是这个。So you can see now the frequency of this apple pendulum. Okay, with the apple at the end of the rod, given the same length of the rod, okay, you find out the natural frequency to be 0.67. And then now, okay, you do the same test with the apple removed. Okay, you find out that the natural frequency of the bounce-outward rod itself is faster. Okay, so here the total mass doesn't appear in the natural frequency. Okay, so that's why you can do the comparison between the two and figure out, oh, my natural frequency of the rod itself is faster. Okay, faster by how much? Faster by this square root of 1.5. Okay, so in that way, you take the ratio. Frequency ratio between the two experiments is 0.8, and then by calculation, and by experiment, the ratio is 0.83. So it's quite close. Okay, of course the difference will be due to the actual length of the apple gravity center is further away from the pivot. So that contributes to the difference. Okay. Okay, after this, now we move on to the next experiment. Okay, the next experiment we're going to have the spring mass system. So ideally, if there is no damping, a mass spring damper will keep vibrating at the same amplitude forever. But you're never going to have this approaching motion because of the presence of the damping. So in the presence of the damping, the amplitude will decay, but you can still see the oscillation. Okay? So what this experiment is, let's have a look on the this is the apple balloon. Okay, a motor-driven slider. Then they're going to start the vibration by force excitation. Okay? So you can turn the motor fast. Okay? You can see the motor is rotating fast. Okay, but the amplitude of the spring does not follow. Okay, so you can see that it's very big at the top and the end. Okay. Okay. So here we only concerned about the this mass spring system. The actual mass spring system is more complex. Let me see if I have other video. Okay. Yeah, I think that's the one. Then we continue the modeling. So in this model, so what is pressure? We're going to have master spring supporting a lump mass. Okay. So this spring we assume carry no mass. Okay. But at the tip of the spring, there is a point mass. 所以我们现在在模拟的是这个弹簧质量系统构成的这个自由振动。OK， 好，我们就先跟大家讲一下你的弹簧质量系统。OK， 一根弹簧 ，OK， 在这个位置，这是它的平衡位置。假设弹簧没有自重 ，OK， 它只是一个弹力 ，OK， 然后你加了一个质量 ，OK， so in this case, we're going to have this what we call static expansion, okay, the static expansion, okay, so. Let's see if you can understand that. You see a video. You see, when I'm doing this, I can let go fast. Okay? So this was the starting position, and if I let go, then you exit. Okay. So meaning, if I'm doing the static expansion, I will use my hand and lower it down gradually, and then until it stay here. So what's the formula you can write about this? You can write about this using the force versus the extension, and this is your gradient. What is the force here? This is your mg here. Okay, so your extension is now your mg divided by the spring constant. So for this section, so you say it's a static loading. Okay, so you have static extension. Okay, and now beyond and this position is what you call equilibrium position. Okay, so called balance position. 所以我们做的这个弹簧线基本上是让弹簧的自重把弹簧拉下来。OK， 所以弹簧自动把弹簧拉下来，这个时候它的伸长量就是所谓的你的静态伸长量。你可以用胡克定理，基本上是力跟伸长量的一个比值。这比值，这条线是一个直线，这个直线的斜率就是你的弹性系数。OK， so that's for the static equilibrium. And then next you use by hand to pull it down. Down from the equilibrium position to a starting position. And this X is what we call a dynamic displacement. Okay? Look at the drawing. It's measure of the equilibrium position. So in this case, your spring gets lengthened. Okay? So this is the starting case. This is the equilibrium case. This is the starting case. So now we're going to write the equation of motion. Okay? Let's see here.好，这个平衡状态的时候，你写的是牛顿第一定律。So what is it? Force sum is equal to 0. So what is the force? There is a weight pointing it downward. Okay? And then it is opposed by the spring force. Okay. Because it pointed upward opposite to the displacement, so this is K delta. Okay? So this is Newton's first law for the equilibrium condition. But now in the phase 2, the phase 1, okay. Now you are not in balance anymore. Okay, you are writing using Newton's second law. Force sum is equal to m x double dot. This is the acceleration. X dot for velocity, x double dot for the acceleration. Okay? And then, what are the forces? Is the weight removed? No, the weight is never removed. So then you're going to have weight there. Is the spring force the same? The spring extension is how much? You go and count. 所以常常它的总伸长量是多少？一个静态伸长量，再加上一个动态伸长量，所以总伸长量是 delta 加 h。OK， 那这是反向的 ，OK。然后这两个力加总在一起，等于什么？等于你的质量乘上加速度。你会问，老师，为什么你这个加速度没有把这个 x 拿去二次微分？你可以把 delta 拿去二次微分。不过这是静态位移，这里 ，OK， 吗 ？So now you have two equations. One equation for the static balance, the second equation for the dynamic motion. Dynamic motion happens when it's being perturbed off the equilibrium. OK， 这个同学看到没有？你们要学的是画这个自由力图 ，OK， 然后再写方程式。你如果没画出它偏离平衡位置，你是绝对写不出牛顿第二方程的。在平衡位置的时候，你就只能写出牛顿第一方程。OK。So after you've got these two equations, okay, let's simplify the equation 2. can see that these two equations are almost identified. Can I have equation 1 minus equation 0? Okay? So if you do this subtraction, then you're going to have n3 being gone, minus k delta also gone, and then what is left is minus kx. And then the right hand side is then going to be equal to nx double dot. So your equation is now simplified to be mx double dot plus kx equal to 0. And then this is your so-called equation of motion. So even though you are writing Newton's second law, but very often we say this is equations of motion. Okay? And next, we're going to release it. Okay? Let's clear up the drawing. And we're going to release it. What happens if we release it? If you not plot it versus time. And this is the position in x. Okay? And you're going to spring back. Going up. Spring back, going up. Okay? Why there is a spring back? Of course you can say this spring is overstretched. It's beyond the equilibrium position. So it will spring recoil back. And once it's reached the equilibrium position, why it keep going? Because at this point velocity is 0. But at this point velocity is maximum. So this velocity will keep it going on to the top until the velocity becomes 0 again. Okay? So this will then convert the kinetic energy into gravitational potential energy. In this case, the spring is under loading. It's less than the weight, and then the weight will pull it down. Okay? The weight will pull it down again to reach the maximum velocity. And then again, this velocity will keep the weight going on. 所以我们这个弹簧，这个运动，来可能解释一下，我们看一下图。Okay, this is equilibrium position. Okay. Okay. But now, okay, rather than waiting it to be extended, then I do the static one. Okay. I let go, and it overshoots. So you can see that the equilibrium position is somewhere at the middle here. Okay, it's oscillating. Okay, after you have obtained this, then let's create one blank page first. Okay, how do you obtain the solution to equation of motion? So you already can see that these free vibrations, if there is no damping, there will be amplitude capital X. What is this capital X? Capital X is on the equilibrium position to the height. Capital X, equilibrium position to the value, the X. Okay? And this is the sine function. Okay? And how frequent this sine function complete a period? Okay? You go and then the time. So this is the 2 pi, the time divided by the period. Okay? Plus the phase. Okay? So for simplification, 2 pi over the period is then defined as sine omega t plus the phase. Okay? If you do time differentiation, then you're going to obtain the velocity. That is omega x cosine omega t plus the phase. Okay? If you differentiate it one more time, then you're going to obtain the acceleration. This is minus omega squared, capital X sine omega t plus the phase. Because you're differentiating cosine function of time, then the derivative will become sine function of time. So you can see that what going to be applied. This is the acceleration term. This is the displacement term. What is common between the acceleration term and the displacement term is this, the amplitude times sine function. Okay? As a result, when you are doing the simplification, you can say, oh, I will take out capital X sine omega t plus the phase, and the right hand side is 0. The first term is mass times acceleration. Mass times the coefficient of the acceleration is then minus m omega squared. And then the second term has the coefficient k. Okay, plus k. Okay. 所以同学看到吗？你们的这个运动方程是牛顿方程，基本上是质量乘上加速度，再加上弹性系数，再乘上这个位置。我现在讲的都是动态位置啦。然后这个动态位置，我们知道它是一个正弦函数，有一个组织 x。然后加速度呢，它刚好跟你的动态位置是同一个表示方式，但是反向再加上一个系数，就是 minus omega。所以因此你在画整的时候，你可以先把你的谱值跟正弦函数取出来，然后把它的系数乘到加速度项的系数，就是负 omega square 乘上质量，然后这个位移的系数是 k。So in this case, then you obtain the equations for the indeed it's a frequency equation for the mass spring system. So here you can observe the free vibration has non-zero amplitude. So in this equation, in this frequency equation, x cannot be zero, and because the sine wave is not always zero, you can also say it's not zero. So the only possibility that the frequency equation is satisfied is this term is zero. Okay, this free multiplier. 乘上这个系数，看这个系数项等于零。So in this case, you can say, oh, my natural frequency is square root is k over m, and then your omega is equal to square root of k over m. So how this natural frequency is determined? If next time you have the equation of motion, you simply can say this is the second order coefficient, this is the zero order coefficient. My natural frequency can be written straight away by writing the zero order coefficient divided by the second order coefficient. 所以以后你们看到微分方程，你们也不用去带这些公式了。OK， 它如果是这个二次微分方程，然后又没有一次项，你就直接把零次的系数当做分子，二次的系数当做分母，取该分号，它就是你的这个角自然频率。OK， so in this case, you do not need to solve for the ordinary differential equation. By simply looking at the coefficient of the second order ordinary differential equation, you can write the natural frequency. So this is not just applied to the term without first order derivative. Even in the presence of first order derivative, this ratio is always of untamed natural frequency. OK， 好，这个清楚吗？ OK， 我们就回过头来看。So we have gone through with you what is static equilibrium. So it's the balance between the applied force and the spring force. Spring force is pointed opposite to the applied extension. Okay, and then next, in the dynamic case, so you have the decay of the extra dynamic displacement on top of the static displacement. So even though the analyzed, but in the end the solution can be simplified into purely in terms of the dynamic displacement. So here you have the equation of motion for the mass spring system. So there is balance between the weight in the direction of the dynamic displacement and in the opposite spring force. So this equation of motion we have the harmonic solution, and the harmonic solution with the angular natural frequency determined from the coefficients. And you can see that coefficients simply square root of k over n, especially the zero order coefficient divided by the second order coefficient. And then take the square root, then you got the natural frequency. 好，所以我们就解的这个单方质量系统。Okay, in this case, you have to find the effective spring constant. To find out the natural frequency, you don't need so. 我们看一下这个是一个摇篮，我们看一下。So this kind of baby hammock is quite common in Southeast Asia. Okay. 所以有看过这样的婴儿床吗 ？OK，
可以自己做一个哦。
这个是取代你爸爸妈妈的椅子 ，OK， 特别适合在夏天 ，OK， 对，现在这里天气比较冷，没有热床 ，OK， 然后问题就来了，我这个宝宝刚出生的不是一个床，属于硬床，是大一点，这大一点的就长得很快。So this is a baby hammock used in Southeast Asia, where the country has a very hot weather. So you have a fabric holding a baby. Okay, but remember, baby will grow fast after 6 months or one year. So the frequency that baby feel comfort is a fixed frequency. Okay, but the baby weight when baby keep growing, okay, a baby can be 5 kilograms. If it grow to 10 kilograms and still want to sleep on the baby hammock, what shall we do to keep the rim of the frequency comfortable to the baby? So you're not going to shake the baby fast. Okay? If it's light, with too much spring, then you're going to have too fast frequency. Okay, so when baby going heavier, then you need more spring. So in the equation, in writing the equation, okay, so you don't need to go for the so-called equivalent equation. Okay, what you have to write is sum up the external force, dynamic force. Okay, of course, if you're going to write fully, okay, you're going to have weight minus the spring force. Okay, and if you now have 1, 2, 3, 4, 5, 5 springs to oppose, then you can go and resolve it. The equation of motion is going to be 5kx. Okay, under the condition that the mg minus k 5k delta is 0. Okay， 所以你在处理这个问题的时候，你可以用简单的用这个方程式去解 ，OK， 然后你就解到，哎，我的这个自然频率在增加这个弹簧的情况底下，哎，它的这个自然频率就上去了 ，OK， 或者是增加重量。